So welcome back to Basil's physics classroom. So I hope you are doing good, all my dear students. So today I have come in before you with a new chapter for the discussion, that is EMI. So I'm actually planning to give you a brief idea about the whole chapter. Okay. So when you think about EMI, what is the first thing that comes to your mind? The first thing that should come to your mind is about the great work done by Michael Faraday and Henry, right? Why? Because when Michael Faraday actually said that a changing magnetic field can create an electric current, the scientific community actually asked him, "Hey Michael, what is the purpose of this? What is the use of this?" But remember that he did not go down listening to all those comments or anything. He kept on doing his work, and now can you imagine a world without the innumerable applications of EMI, electromagnetic induction? So what is actually electromagnetic induction? So electromagnetic induction is actually the phenomenon of generating an electric current by varying the magnetic field. To explain that, Michael Faraday actually did a few experiments. The first experiment was that he took a coil, he connected a galvanometer to it, okay, and he took a bar magnet, a north and a south pole, right? And you know that magnetic field lines form closed loops, unlike an electric field lines which start from a positive and ends in a negative, right? So the first experiment what Michael Faraday did was he actually moved the bar magnet in and out of the loop. So you know what he observed? He actually observed a deflection in the galvanometer. Now when he moved it inside, he observed a deflection, and when he moved it outside, he actually observed a deflection in the opposite direction. Alright? So this had him thinking, what is happening there? So now again what he did was, he took one more coil, and he was passing a current through the coil. There was a current through the coil. Fine, a battery is connected and a current is passing through the coil. Now, he was moving this coil up and down, up and down. He was moving this coil. So again what he observed was that there was a deflection in the galvanometer. So when he moved it towards the coil, the deflection was in one direction. When he moved it away, the deflection was in the opposite direction. So he understood that because a current is flowing through this conductor, there will obviously be a magnetic field around it that you have learned in the last chapter, right? And because this is moved with relative to this coil, we can say that the magnetic field lines linking with this loop is changing. Or we say that the flux associated with this loop is getting changed. So I am telling you a new term there, flux. So what do you mean by flux? Or we can call it as magnetic flux. Now flux is actually the total number of magnetic field lines crossing a unit cross-sectional area. Alright, so the flux is given by magnetic flux. In electricity also we are defining a flux, the electric flux, right? Magnetic flux phi b is given by phi b is equal to integral b dot dA, or you can also write like this is equal to b dot a. So dot a, it's a dot product of two vectors. Which vectors? Magnetic field and area vector. You can actually expand this and you can write it as phi b is equal to ba cos theta. Now what is theta? Theta is the angle between the area vector and the magnetic field. So if flux has to be maximum, what should be the value of theta? What should be the value of theta? Theta should be? Yeah, theta should be 0. What is cos 0? 1. So it is maximum. And for flux to be minimum, theta should be 90 degree and the corresponding flux will be 0. Clear? So magnetic flux actually refers to the number of magnetic field lines crossing a unit cross-sectional area. Right? And what will be the unit for this? The unit is actually Weber. Unit is Weber. Or you can also use the unit Tesla, meter square. That's another unit for magnetic flux. So what Faraday proposed was that whenever the magnetic field associated changes. Or we can say it like this, whenever there is a rate of change of flux associated with a coil, there will be an induced EMF. So a rate of change of magnetic flux causes an EMF to be induced. So we can write like this, E is equal to minus d phi by dt. Now what is the meaning of the negative sign? I told you that when Faraday did this experiment, he actually noticed moving towards and away. Deflection was in the opposite direction. So this negative sign indicates that the EMF is induced in the direction opposite, or in another way, which later on Lenz verified like this. The induced EMF is induced in such a way that it opposes the cause for it. So I told you what is the cause or what is the reason due to which induced EMF is generated. How is an induced EMF generated? It is generated when there is a change in the flux associated with the coil, right? So to oppose that cause, the EMF will be induced. That is what Lenz actually proved based on using conservation of energy principles and everything. Lenz actually later on verified that. So we can write E is equal to minus d phi by dt. Now in this statement, we can just replace phi. So d by dt of, if there are n number of terms, I can write n, our term BA cos, instead of theta I'm going to write omega t. We know that theta is equal to omega t, right? So now, when number of turns changes, the induced EMF can change, but let me tell you that is not a feasible solution. Okay, we cannot take the coil every single time, change the number of turns. That's not a feasible solution. And also, if the number of turns is very large, means the device becomes very bulky. In this world of miniaturization, we don't actually prefer that. Okay, so the better is I can take n outside. So n d by dt of either B can change, then there is an induced EMF. If A changes, there is an induced EMF. If omega t changes, there is an induced EMF. So in one way we can write like this, minus n, I'm taking B and A outside, assuming they are constant. So cos theta 1 minus cos theta 2 divided by delta t. That's one way of representing that. Or you can write it as minus n A cos theta or omega t, whatever I'm taking outside, B2 minus B1, okay, divided by delta t, right? Or you can write it as minus n B cos omega t A2 minus A1 divided by delta t. So just understand that out of these terms, B can change, no problem. Area can change, no problem. Cos omega t can also change. And in all the cases, there will be an induced EMF, and that is what Faraday, along with Lenz, verified. So an EMF is induced when there is a change in the magnetic flux associated with a coil. Alright? Now, suppose a coil that I am considering is moving. If the coil I'm going to consider as moving means we will have to account for motional EMF there. So let's see about motional EMF now. Alright, so motional EMF. So when a conductor is moving in a magnetic field, we have to learn about motional EMF. Now, from this topic, questions have appeared previously, okay? So, I will tell you the region from where the questions appeared towards the end. So, motional EMF means when a conductor, when a current carrying coil, suppose the length of the coil be L, okay? It is actually moving inside a magnetic field. Suppose there is a magnetic field into it. A magnetic field into it. So, a conductor is moving in a magnetic field, okay? So, assume that it is a uniform magnetic field, okay? So when this conductor is moving in a magnetic field, an EMF will be induced in it, which is given by E is equal to BLV. E is equal to BLV. Now suppose the conductor is not actually perpendicular to the magnetic field. then the condition will be a little bit different. Suppose this is my magnetic field. The direction of the magnetic field is this. It is making an angle, certain angle, theta with respect to the magnetic field. It is making a certain angle, theta with respect to the magnetic field means, then I can write it as the induced EMF E is equal to BLV sine theta. Induced EMF will be equal to BLV sine theta. So when it is moving perpendicular to a magnetic field, the induced EMF is BLV, and when it is making an angle theta with respect to the magnetic field, induced EMF is BLV sine theta. Now another example is, suppose I have an inclined plane. I'm actually trying to draw a three-dimensional figure, may not be very accurate. Now there is a rod here. This rod is moving down the inclined plane. Now to find the induced EMF here, we will have to take into account the principles you are learning in laws of motion chapter. Okay, so utilizing those principles, we get that the induced EMF in a rod moving down an inclined plane is given by E is equal to BLV cos theta. E is equal to BLV cos theta. Clear? So induced EMF in a which is moving down the inclined plane is equal to BLV cos theta. Now, previously even for JEE means examination, a question has come like this. Suppose we have a rail track. Okay, so what is the induced EMF across along the axle of the train? So a train is moving, this is tire. What is the induced EMF across this? And in the question, the width of the rail track will be given, so that will be equal to the length of this conductor. So here we can make use of the equation in the railway question, railway problem, train question. We can make use of the equation E is equal to BLV. Similar to this, sometimes a question may come, aeroplane is flying in a vertical magnetic field which is caused by the earth. Now, what is the induced EMF across its tips of its wings? So, in a plane, maybe this is a plane, okay. So, this is what you can call it, the wings of the plane, and across the tips, what is a magnetic field? Again, you can take this, the wingspan will be given to you in the question. So again, you can use the equation E is equal to BLV, and the vertical component of magnetic field necessary to find out the induced EMF in case of a plane will also be given. I'll have to write it as a plane, I guess. Okay, anyway. So E is equal to BLV again. Now, I told you that the conductor is in a magnetic field, right? Now, in the previous chapter, you have actually learned that when a conductor moves in a magnetic field, it actually experiences a force, right? And what was the equation for the force? Remember? Force is equal to B I L, right? Or ILB. Force is equal to ILB. I'm assuming that it is perpendicular to the magnetic field. Okay. So ILB. Now, force is equal to ILB. How can you write the equation for current here? Suppose the resistance of the rod is R. Okay, so you can write, according to Ohm's law, I is equal to V by R, right? Or E by R. So we can write it as B E L by R. And what is E? BLV, right? So we can substitute it like this and we get B square L square V divided by R. The force experienced by a conductor moving in a magnetic field, we can write it as B square L square V by R also. Now, once we have the force, we can actually find out the power. What is power equal to? F dot V, or simply I'm going to write it as Fv. Now, power is equal to Fv means F we can substitute it over here. So we'll be getting B square L square V square by R. Now, this power will be dissipated in the rod as heat. Okay, so even if you use the equation power is equal to I square R, will be arriving at the same equation. So the power will be dissipated in the rod as heat. Clear? Now, let me take the case of a rod which is rotating in a magnetic field. So this is a straight rod and it is moving in a circular path. This point is hinged. So this rod is actually rotating like this. It is rotating in the magnetic field like this. Okay. So when this rod is rotating inside the magnetic field, there is a magnetic field. I'll draw the magnetic field also. It's a uniform magnetic field. Okay. So when the rod is rotating in a magnetic field, the induced EMF is given by E is equal to half into, let the length of the rod be L, half B L square. Instead of we have used L here, so no problem. Half B L square omega. What is the equation? Half B L square omega. What is omega? You know that omega is equal to, either you can write as 2 pi by T. Omega is what? Angular frequency. T is the time period of rotation. Or you can write omega as 2 pi F. What is F? F is the frequency. Fine. So half B L square omega. Right. And the same equation can actually be applied in a few more cases. For the first one, suppose we have the question, it is a previous question actually. A cycle is, this is a cycle wheel, and as you know, a cycle wheel has many spokes there. So this is a cycle wheel. They may ask you what is the induced EMF between the center and the rim. So this induced EMF, I'll take this as R. So what will be the induced EMF across this? This is actually similar to the case of this, right? So here also we can write E is equal to half B, instead of L I'm using R square omega. Same thing, no doubt, no change. Okay. Another place we can apply the same condition is in case of a Faraday's disc. So a disc means it is actually consisting of uncountable number of spokes, right? All the spokes are put together, we cannot actually find the correct number or anything. So it actually consists of uncountable number of spokes, and across this point and the rim, we can say that in case of Faraday's disc also, E is equal to half B R square omega. Again, the same thing. In another cases, in case of a semicircular loop, which is rotating in a magnetic field. A semicircular loop is here. It is actually rotating in a magnetic field. When a semicircular loop is rotating in a magnetic field also, the same condition applies. E is equal to half B R square omega. So in all these equations, in case of motional EMF, these questions can come for your exam also. Motional EMF, the induced EMF is given by half B R square omega. Okay, so I hope that motional EMF part is clear for you. Right, so we started off with BLV, we are using these equations also. Okay, so don't worry, if you want to know how these equations come, I'll be putting a detailed class for all these things, so you can watch it later on, you'll be able to follow this. Okay, I'm not going to the derivation part or anything right now. Okay, so now let's move on to the next part of the chapter, and that is about inductance. Alright, so now we are moving on to inductance. So what is actually this inductance term? Inductance. Now when you talk about inductance, this is actually something similar to the inertia in mechanics actually. Now inductance is actually the method of generating an electric current by the change in flux in one coil. By the change in a current in one coil, there is an associated magnetic flux change coming there, and because of that inducing a current in another coil or the same coil, we are actually calling it as inductance. Okay. Now, since I said it is similar to that of inertia, it means it is something which opposes a change. Okay. An inductor actually tries to decrease the current if it sees an increase in the current. It tries to increase the current if it sees a decrease in the current. So vice versa, it works in both ways. So it is actually playing the role of inertia in mechanics. Okay. So when you talk about inductance, I have to mention very important thing that please remember that the flux is actually proportional to I. And I really hope you know that, right? So flux is proportional to I. So remember that for the first, as an introduction itself, remember that flux is proportional to I. Now, flux is proportional to I. We are very clear about that. Now, you have to remember that there are two types of inductance. One is self-induction or self-inductance, and the other is mutual induction. One is self-induction, the other is mutual induction. Okay. Now, when you talk about self-induction, just like I just said just now, it is the method of inducing current in itself because of the change in current associated with it. So when a current flowing through the coil is changing, it actually induces an EMF on the same coil itself. That process is known as self-induction. Sometimes we also refer to as a back EMF. We also call it as a back EMF. Okay. Mutual induction, as you can say, there is a mutual means two coils are involved there. Okay. Like the experiment done by Faraday. Two coils are involved there. So that is a case of mutual induction. So let's see one by one. So first, let me talk about self-induction. So self-induction or self-inductance. Now, in self-induction, remember that there is only one coil involved there. So here we can write, supposedly it's a coil I'm talking about, and there should be n number of turns for the coil. So I can write n phi is proportional to I. And removing the proportionality sign, I get n phi is equal to Li, where L is known as the coefficient of self-inductance. L is known as the coefficient of self-inductance. L is the coefficient of proportionality we are putting there. So from this, it's very clear that we can write our induced EMF E as this. We already know that E is equal to minus N d phi by dt, right? So here we can also write it as what? Minus L di by dt. So whenever there is a change in the current associated with a coil, there is an EMF induced. And in case of self-induction, we call it what? We call it by the name back EMF. Okay. Now, suppose we are having a solenoid, a single solenoid. Now, the induced EMF here, the inductance L value here will be given by mu 0 into mu r. We use it on mu r only if there is a medium rated there. It may be soft iron core or something. If it is there, we will use mu r. Otherwise, we don't use mu r. Mu r into n square AL into n square AL, small n. It is actually the number of turns per unit length. Small n is the number of turns per unit length. And area is the area of cross section of this coil. Okay. And some other important results are also shown on the screen right now. So you can learn that also. Alright. Now moving on to the next one, mutual induction. Now mutual induction, when you talk about that, the coil can be arranged in any fashion actually. Okay, let me consider two coaxial coils. Now very important thing to remember here is that when a current is flowing through this coil, there can be induced EMF in this smaller coil. When there is a change in current in the smaller coil, there can be an induced EMF in the other coil. So we can say that here, based on reciprocity theorem, M12 is actually equal to M21. The meaning is, whatever be the induced EMF, this one is inducing an EMF in the smaller one, and the smaller one can induce a EMF in the capital one, a bigger one. Whatever that value is, remember that the mutual induction of 1 on 2 is equal to the mutual induction by 2 on 1. Right? And the theorem, we call it what? We call it as the reciprocity theorem. Okay. So here, for this typical example, we can write that the value of M. Now M is known as coefficient of mutual inductance. M is known as coefficient of mutual inductance. Okay. So similar to how we wrote previously, you can write N phi is equal to M I, just like we did previously, or you can also write it as E is equal to minus N d phi by dt, which is equal to minus M di by dt. Fine. Right. So we can write, in case of this kind of an arrangement of coaxial solenoids, we can write it as M corresponds to mu 0 mu r, okay, into N1 N2. N1 N2 I'm writing. I'll write smaller. N1 N2. What is N1? N1 is the number of turns per unit length for the first coil. N2, the number of turns per unit length for the second coil, right? Into AL. Now, one thing you have to remember here is, whichever value you are taking, M12 or M21, A remains the same. A is actually the area of the loop inside. Just remember like that, so you won't get it confused with. Okay, A corresponds to the area of the loop which is placed inside. Okay, so or we can say the smaller loop associated. A corresponds to that. Okay, so remember that. So these two formulas are very important. Mu 0 N1 N2 AL, and in case there is a medium, mu R also is there, and self inductance is given by L is equal to mu 0 mu R N square into AL. Clear? Right. Now let's see what is the condition when two the so-called inductors are connected together. 1 and 1. As you can see very clearly from the figure, it is a series combination, right? It is a series combination. So if they're connected in series, we can write it like this. We can write it like this. L equivalent will be equal to L1 plus L2. But this condition holds only when these two are far apart. Fine. When they are far apart, this condition holds. Else we'll have to take into account the mutual induction also. So we can write like this. If they are close, we can write like this. This is far apart. Close, we can write L is equal to L1 plus L2 plus or minus 2n. Alright. Now suppose they are arranged in parallel combination. If it's a parallel combination means, how do you write? This is parallel. How do you write for the parallel combination? In general, 1 by L is equal to 1 by L1 plus 1 by L2. When do you write this? When do you use this? When they are far apart. Okay, and they're close by, we have to use, when you simplify this, what you get? L is equal to L1 L2 by L1 plus L2, right? So L is equal to L1 L2 minus m square divided by L1 plus L2 plus or minus 2n when they are close. So please do remember this. Okay, generally you will have to use this equation only for series and parallel combination. Okay, you will not have to worry about much this other than in case of a JEE entrance exam. Okay. Now, one more additional point you have to remember here is, in case of a mutual induction, there can be a self-induction also taking place here. So we can write a relation between mutual induction and self-induction like this. M is equal to K into root of L1 L2. M is equal to K into root of L1 L2. Where L1 is a mutual inductance, the self-inductance of the first coil. L2, the self-inductance of the second coil. Alright. Now, coming back, K. K is known as the coefficient of coupling. Coefficient of coupling, or the coupling factor. Now K actually can vary from 0 to 1, and K is equal to 0 means minimum coupling, and K is equal to 1 means the coupling is maximum. Okay. Now usually the K value will be given to you in the question. Okay, or if it is not, you can just find it like this. K is equal to the magnetic flux linked with the secondary by the magnetic flux linked with the primary. K is equal to the magnetic flux linked with the secondary divided by the magnetic flux linked with the primary. Okay, so K is a coupling factor there. Clear? Any doubts there? Alright. So one more thing to mention here. That's about the potential energy involved in an inductor. So the potential energy or the magnetic potential energy is given by U is equal to half Li square. Okay, and if it is magnetic potential energy density or a B square by 2 mu 0. What is that? B square by 2 mu 0. Okay, so the potential energy or the work done is given by half into Li square, and U is equal to the, what is U? Energy density, that is energy per unit volume, that's it. Energy density is given by B square by 2 mu 0. Alright, clear? Any doubts? Right, so if you have doubts, please feel to comment below. Alright, okay, now we are moving on to learn about a transformer. Okay, so I think one more thing I have to remember here is, I told you that the minimum value K can be 0, the coupling factor, and for coupling to be maximum, it is very necessary that the coil has to be wound over each other over a ferromagnetic core. In such a case, the coupling will be maximum. Okay, so we do prefer a winding over a ferromagnetic core to have maximum coupling, right? So now moving on to the transformer. Now, transformer, it's something which we actually are familiar with and we use in our day-to-day life, right? So if I ask you, have you used a transformer today? What will be your answer? What will be your answer? Have you used a transformer today? I'll tell you, yes, you have used. I've actually close to use 3 times or something, a small transformer. What is that? Yeah, inside my charger, which I used to charge my phone or something for other purposes, we have a small transformer. It's a step down transformer. In the electricity that comes to a house, we know that high voltage lines are there, like 22 kV lines, 11 kV lines, and everything is there. And what the voltage requirement at a home is something only around 230 volt, 240 volt, around that. Okay, you can just check your electronic meter, it will correctly display what is the present voltage and everything there. Okay, so to bring the voltage down, we are making use of a step down transformer there. Sometimes we need a step up transformer. Near my house there is a mill, and since there a lot of processes are taking place there, they require a high, some voltage fluctuations will occur. Therefore, the people have asked for a new transformer to be put so that it can be stepped up. So there can be a step up transformer, there can also be a step down transformer. Right. So a transformer, one thing you have to remember in a transformer is, it is only stepping down the voltage or the current. It can also step up the voltage or the current, fine. But there won't be any change in the frequency of the input and the output of a transformer. Okay. Now we make use of that in TVs and everywhere. We can actually make use of a transformer. So remember, there is no change in the frequency. However, there is a change in the voltage that will occur. So let's see. So in a transformer, normally it's one kind of a transformer. So I'm actually winding. I'll show you a different one, a simpler one, a simple transformer. It's a simple transformer. Okay. So now, so there is something known as a transformer ratio you have to remember about. Now, transformer ratio means NS by NP equal to Vs by Vp is equal to Ip by Is. Actually, this is what you have to remember when you talk about a transformer. Okay, keeping everything aside, everything else aside, this is what you have to remember. The transformer ratio, Ns by Np equal to Vs by Vp is equal to Ip by Is. Right? So this is what you have to remember there in case of a transformer. Now, suppose you are asked to find out the number of, what is Ns actually? Number of turns in the secondary, Np, number of turns in the primary, Vs, voltage of the secondary, Vp, primary voltage, Ip, current in the primary, Is, current in the secondary. So this first one, this is called as the primary, and the second one we call as secondary. Now they need not always be like far apart or anything. Okay. Now sometimes it's like I mentioned, for coupling to be highly efficient, to minimize the magnetic flux leakage which may occur here, we usually wound it along the same cord. So don't get the idea that they will get short circuit or anything. They won't. There will be a thin layer of insulation deposits over there, over the wire. So there won't be any issues of short circuit or anything. Normal. Okay. Now, So remember this transformer ratio, you're bound to get some questions from there. Okay, so in case of a step up, if it is a step up, what will happen? Let's see. If it is a step up transformer, step up means making the voltage notch higher. That is meant by step up. So step up means Vs is equal to, from this ratio we can write Ns by Np into Vp, right? So now if it is a step up transformer, from this condition it's very clear that the number of turns in the secondary should be greater than the number of turns in the primary. The number of turns in the secondary should be greater than the number of turns in the primary. Then only we can call it as a step up transformer. Okay. Now it is step down means what? Step down means yes, the number of turns in the primary should be greater than the number of turns in the secondary. Is the point clear? So step up and step down. I'm not writing step down there. I hope you have understood the point. Okay, step up, Ns is greater than Np. Okay, just remember one side, you'll be able to remember the other one. Right. So that is about a basic idea about a transformer. So in a transformer, it's very necessary to limit the heat losses and everything. It's a coil, it may get heated up. So it is really important to minimize the heating loss, to maximize the flux linkage, it is essential. And all those things are very important here. Okay, in case of a transformer. Now moving on to the last topic related to EMI, that's about eddy currents. Okay, so it's actually a theoretical topic. I would say that you have to read through your NCERT thoroughly for this topic. Okay, only 2 pages are there in NCERT. Please go through that, eddy currents. I'll just give you the idea. Now, eddy currents means actually whenever I have suppose I have a bulk material here, and for this bulk material, the magnetic flux associated with it is changing. So you know that whenever the magnetic flux is changing, what will be there? Yeah, there will be an induced EMF, right? So when there is a magnetic flux change, there will be an induced EMF and a current will flow. And this current, we actually call it by the name eddy current. And this is known as eddy current because it actually flows like eddies in water. Okay, and there is another name also for this. Foucault current also it is known. Foucault current, it's also known as like that because he was the person who actually discovered that. So eddy currents. Okay, so it is in the bulk of the material. Now the problem is, suppose a current is flowing in the bulk of the material. So you know that when there is a current flowing, there will be heating effect. X is equal to I square RT, right? It gets heated up, which means a lot of power is wasted there because of this eddy current. So it is not actually very desirable. In case of a object we are using, it's not always very desirable. But as humans, we make use of everything around us, right? So what do we do is, to reduce this eddy current, what we use is, we can make holes, thereby increasing the resistance there and decreasing the current. Or we can make small slots like this, slots in the material. Or we can actually do another thing, we can do some lamination for the process. Okay, so when you take a normal motor, mini motor, if you have it with you, you can take a small mini motor, open it up, you can see that there is a coil. Inside the coil, the small plates will be there. They will actually be divided into small parts. The reason is to minimize the eddy current, to minimize the heating effect. Now, we have actually made use of this eddy currents. We make use of that in furnaces where heating is needed. Okay, and I think you have heard about something else, a deadbeat galvanometer. Normally, in a galvanometer, what happens? When there is a current flowing through here, the needle actually deflects, right? And once we remove the current also, it cannot come back to its mean position all of a sudden. So it may just oscillate like this. So in order to make it a deadbeat galvanometer means, the instant we remove the current from the circuit, the galvanometer comes back to its main position. That is a deadbeat galvanometer. We can use that all there. In braking of trains, we are using eddy currents, effects and everything. Okay, so please read through NCERT for more details on eddy currents. I have just given you a brief view on that. So please read through it. Okay. Alright, so that is the basic ideas about EMI. I hope you have understood the topics I have taken today. And if in case you have any doubts, please do comment below. And any chapters, if you want, you can comment below. I'll be very happy to take it for you. So please subscribe the channel, and for further notifications, you can click on the bell icon there at the bottom. So please do it. And till next time, signing off.